Hello everyone, welcome to DP Tutorials by Donny Jerwa. In this teaching module, we will learn on another important application of Ampere's Circuital law, and this is related to determining the magnetic field due to a toroidal solenoid, or in short, we define this as the toroid. Okay? So what is a toroidal solenoid? If I have a wire and if I wrap this wire on a cylindrical material and such that all those wrappings form closed rings, then such type of arrangement is what is known as your toroidal solenoid. Okay, that is known as your toroidal solenoid. So what is the definition of a toroidal solenoid? It is nothing but there are two definitions I have marked over here. The first one is that it is in the form of a ring. A solenoid in the form of a ring is called a toroid or a toroidal solenoid. Now, the second definition, the toroid is basically what? It is an endless solenoid in the form of bending which is formed by bending a straight solenoid so as to give what? So as to give a circular shape. So over here, this is a solenoid which you have seen, and over here also, through one end of the solenoid, that means current will enters. Say like for instance over here, the current enters to this point and the current leaves to this point. Okay, in which these arrows indicates the direction of movement of current. So it is very obvious that this particular end of the solenoid where the current enters, that particular end of the solenoid where the current enters, that will behave, this end of the solenoid will behave as what? This end of the solenoid will behave as the south pole. And this particular end of the solenoid where the current leaves, okay, indicated by this arrow, this particular end of the solenoid where the current leaves indicated by that arrow, this particular end of the solenoid will behave as what? Will behave as the north pole. So that is why the current in this case, okay, the current in that case always moves from north to south. So that is why the direction of this magnetic field is indicated by these arrows, and the direction of this magnetic field is indicated by this arrow. So the direction in this case of the current up as per this current flow, the direction of the magnetic field will be clockwise direction. Okay, it will be clockwise direction. So this will be that means we know when current is passed through any conducting wire, there will be a magnetic field produced by that wire. So this is the magnetic effects of electric current. And also we have studied in a solenoid that the strength of the magnetic field is very large for regions inside the solenoid or for regions inside the toroid. It goes as well for a toroid. And the regions of the magnetic field will be lesser or negligible for regions outside it. If you consider, if you take for instance, for suppose a point X which is located at this particular point, okay, suppose from here we have this toroid which is in the form of a circular ring, and I consider that point X, okay, which is at a certain distance. Suppose if this is the center of the toroid, that means at a certain distance. So from here, the magnetic field at this point X will be very small or negligibly small. If I consider another point, say another point over here Y, which is inside the toroid, so the magnetic field over here will be what? Will be very large. And if I consider suppose a point, suppose say like Z, which is in the interior of the solenoid, that means over here the magnetic field will be also negligibly small. So that is why if I have a toroid of this form, that means I know that if I want the magnetic field to be large, so it depends also upon what? The number of turns, and also it depends upon the current I which passes through what? Which passes through this toroidal solenoid. So from here, this is a toroidal solenoid in which the current enters from this end and it leaves this end. So which means that this end of the solenoid will behave as the south pole, and this particular end of the solenoid where the current leaves, that will behave as what? That will behave as the north pole. So that is why the magnetic field, okay, the magnetic field inside the solenoid will be in this direction. So that will be the direction of one of the magnetic field inside the toroid, okay, inside the toroid, indicated by that direction. So it is always from south to north. Okay. Now we will go on into the description or derivation of that particular heading. So from here, let us assume, okay, let us assume that we have this toroid having a large number of turns, and of which is of the form of circular, which is wound on this circular ceramic material. So this is that which we have written over there. This is that circular ceramic material. So over here, this is your ceramic material. Okay, so that is your ceramic material. So I will not. So this is that ceramic material. Even this, okay, this ceramic material is that which is in your yellow form. Now let I be the current flowing through the solenoid. Okay, let I be the current flowing through the solenoid, and let the total length of the solenoid. If I have the total length of the solenoid, since there are n number of turns, okay, since there are n number of turns, okay, total number of turns in this case will be capital N. Okay, it will be capital N. So over here, the total number of turns, let capital N be the total number of turns. And from here, if if small l is the length of that solenoid, that means from here, if L is the length of the solenoid, then the number of turns per unit length, that means total number of turns divided by the length of the solenoid, capital L, divided by the length of the solenoid, capital L. This will be defined as what? The number of turns per unit length, denoted by what? Small n. Now, what is this total length of the solenoid? See, like for instance, from here, if I want to take the total length of the solenoid, that means I have to take with respect to what? I have to consider this area of the solenoid. Suppose if R is the radius of this toroid, okay, if R is the radius of that toroid, then we know that it is obvious that the circumference of the solenoid, which is twice pi r, okay, the circumference of that toroid, which is twice pi r, this will be what? This will be give us the length of the solenoid. So from here, if L is the total length of the solenoid, then this total length of the solenoid will be equal to 1. It will be equal to twice pi r. So those are the important things. Now, I have also explained, okay, I have roughly explained over here some of the important cases with respect to what? With respect to finding the magnetic field, okay, with respect to finding the magnetic field due to a toroid. See, okay, let me just recall again, or let us rephrase again. We have to consider points which are outside the toroid, okay, points which are outside the toroid, points which, say, if I take this as point P, if I consider another point within the toroid which is point Q, and if I consider a point R which is inside the toroid, and this is one, this is the center O of the center O of the toroid. Then over here there are 3 points, point P, point Q, and point R. This point Q is on the axis of this toroid. It is obvious that if I want to find the magnetic field at point P, that means I have to consider what? I have to consider or construct Amperean rule. Okay, I have to draw or construct Amperean rule. So from here, also another important point that we need to ponder upon is that you have to focus. You have to focus on the direction of movement of current. See, when this current enters this toroid through this point, that means it will goes from here. That means this particular end where the current enters, or goes through the toroid, that particular end will be marked by what? Will be marked by cross point. So it will be marked by cross point. And from here, see, the current, it goes and then it comes out from this particular point. Once it comes out from this particular point, that means the current will move out. So it will be represented by dot. In this case, then it comes out, and then from here it moves, it goes inside. So once it goes inside, in that part, at this particular point, that means since it goes inside, it will be represented by cross. Then from here again it goes, and then from this particular point, okay, from that particular point, the current comes out, so it will be marked by dot. So that is why if I redraw, if I resketch this this toroidal solenoid in this form, in which this outer this outer circle will represent this part, and this inner circle will represent this part. So from here, along this inner circle, all along the inner circle, this will represent the point where the current goes inside. So all those cross, okay, all those cross indicates, all those cross indicates the current which goes inside the solenoid, okay, which goes in. And from here, all these points, see, it goes inside and then it comes out from here, represented by that. Then it goes inside, represented by this cross. Then from here, it comes out. Okay? Then again, it goes inside. This will be represented by cross, and then it comes out from this particular point, dot. Okay? Then again, it goes inside. This will be represented by cross, and then it comes out from here. That means it will be represented by dot. So that is why all these outer cylinder, all this outer circle will be represented by dot. All these dots, all these dots represent the part of the current which comes out. The part of the current which comes out. So from here, I want to find out what is the magnetic field for points which are inside. See, if I consider the point, suppose for a point P which is outside the solenoid, and for a point Q which is inside the solenoid, and another point, suppose a point S. Okay? Let this point S be the point which is inside, this is inside the toroid, and this is for regions in the interior of the solenoid, in the interior of the toroid. So there are 3 points. This is the first case for points outside the toroid. This will be the second case for the point which is inside the toroid, and this point S will be the third case for which we want to find and determine what will be the magnetic field for all these 3 cases. Point P which is outside the toroid, point Q which is inside the toroid, and for point S which is in the interior of the toroid. So it is obvious that magnetic field will be more on the interior of the solenoid. So from here, say, like for instance, if this, let P be the point which is outside the toroid, okay, let this point Q be the point which is inside the toroid, okay, let me name this as point S. Let point S be the point which is inside the toroid. This is the point P which is this is the point P which is outside the toroid, point S which is inside the toroid, and this point, suppose like that point Q which is what, which is in the interior of the toroid. Then what I have to do in order to find the magnetic field across this point P? Then what I have to do? I have to construct this Amperean loop, which is of the form of what? Of a spherical surface. So that is the way how to do. Okay, so we will consider those Amperean loop. We will consider this Amperean loop in order to find out what? In order to find the magnetic field due to those points. Okay, point P, point Q, okay, point P, point Q, and point S. Okay. So from here, this will be point Q, and this will be what? This will be point S. Let this be point Q, and let this be point S. So all these points are similar to these points, which represent the current. All these are nothing but what? All these are nothing but it represents cross, represents the part of the current which goes in. Okay, part of the current which goes in, and from here it comes out. Dot will represent the part of the current. Dot will represent the part of the current which comes out. So from here, so in order to find the respective magnetic field through those points P, Q, and S, we have to consider these Amperean loops. So I will take these Amperean loops, with respect to that point S. I will take this Amperean loop and construct over that particular point. Then with respect to this point P, I will take another Amperean loop, and then I will construct across that point. Then with respect to this point P, I will take another Amperean loop, and then I will place it over there. So these are the loops. Okay, these are the loops. So from here, that means these are what? These are your Amperean loops. Okay, Amperean loops. For loops, for loops, I will consider this as loop number 1. Okay, this will be the first loop. Okay, I will write this as the first loop. For loop for this spherical surface with respect to point P, this will be the first loop. Okay, that will be the loop 1. Then this with respect to point Q, this with respect to point Q, this will be what? This will be the second loop, and with respect to point S, let this be one. Let this be the third loop. Then from here, there will be different radius. Let's pay attention. Let this radius be, suppose let that radius be R3. Then with respect to this second loop, drawn across this point Q, this second loop drawn across this point Q, that means let the radius be 1. Let this radius, okay, let that radius with respect to that point Q be R. Okay, let us write as R. So let this radius, okay, let that radius be R. Then this radius with respect to the third loop, let that radius with respect to the third loop be R3. Okay, and with respect to this first loop across that point P, okay, this radius will be 1. Let this radius be R1. So that radius will be 1. This will be R1, radius R1. So we have different radius. Radius R1, radius R, and radius R3. So over here, due to the first loop, due to this second Amperian loop, this is the second Amperian loop with respect to this point Q on the interior surface, okay, on the interior surface of the toroid. So the radius of that toroid, the radius of the second Amperian loop inside will be R. The radius of the first Amperian loop is 1. The first Amperian loop is R2. So over here I will write, or R1 I mean. And for this third Amperian loop, for the radius of the third Amperian loop, that means this will be 1. This will be R3. Let R3 be the radius of the third Amperian loop. So in order to determine the magnetic field across the toroid, we construct what? We construct these circular Amperian loops 1, 2, and 3 drawn by dashed lines. Okay, draw all these by dashed lines. So I will name this as figure number 2. Okay, this is the figure 2, and this one, okay, let that be 1. Let that be the figure number 1. Then from here, you have to represent, okay, the line integral. So in order to find the magnetic field, so it will be the contribution due to the magnetic field. It will be the contribution due to the magnetic field from point P, the contribution of the magnetic field from point Q, and the contributions of the magnetic field from point 1, from point S. So that is why over here you have to consider what? The line integral. So the line integral over here, the line integral of the magnetic field of B dot dl, okay, the line integral of magnetic field B dot dl is given by, okay, so this will be B dot dl dot product. Then you have to consider the contributions of the magnetic field due to, okay, loop 1, due to the first loop, due to loop 1, B dot dl. This is the first loop. Then you have to consider the line integral of the magnetic field due to 1, due to the second loop, okay, second loop with respect to point Q, B dot dl. And also you have to consider the magnetic field due to the third loop. The third loop, this smaller circular Amperian loop. So line integral of the magnetic field due to 1, due to the third loop. So this will be 1. This will be the integral inside will be B dot dl. Okay, B dot dl. So let us mark this as equation number 1. Let us mark that as equation number 1. So it may be noted that the current, it may be noted that there will be no current. Okay? There will be no current across point P. There will be no current across point S. Okay? Point P and point S. So over here, see, if you look from that diagram, okay, if you look from this diagram, okay, I have written in such a way. Okay, I have written in such a way that if, okay, if this point P is point outside, so there will be no current. across point P, okay, in which that Amperean loop is constructed. If I consider this point S, if I consider that point S also, which is inside, even over here also there is no current. The current will be enclosed, the current through that point Q, which is inside the toroid, only that will be the current, only that point will be the point which the Amperean loop encloses the current inside. Okay? So it be noted that the current does not pass, okay? Does not pass through what? Through the loops 1 and 3. Current does not pass through that loop 1 and 3. So from there, it is very obvious, okay? It is very obvious that the current, let I1 be the current in the first loop, so it will be 0. That current will be 0. And in the loop number 3, that means the current I3 also will be 1. The current I3 also will be equal to 0. Okay? So from here, if you apply Ampere's Circuital law, for the respective loops, so the equations will be in this form. Okay? So for the loop 1, okay, closed integration, this will be the first loop. That will be the first loop number 1. So this will be line integral of B dot dl. This will be equal to 1. Mu naught, according to Ampere's Circuital law, the line integral is equal to mu naught times the current. So since it is for the first loop, so the current which we have represented over here, it will be what? It will be I1. So from here, since we want to find for the magnetic field B, then the magnetic field B is always constant, so we can take outside of the integral. So this will be the 1. This will be integral 1, line integral of 1. Line integral number 1 of dl. This will be equal to mu naught. What is the value of I1? The value of I1 is 0, so that is why I've substituted over there. Then over here, okay, we will get, this will be into, then from that circular loop, if we look from that circular loop with respect to I1, with respect to the line integral of the first loop, with respect to the line integral of this first loop, that means if you take summation over dl for the first loop, okay, this will be equal to the circumference of that loop, which is equal to what? Twice pi r1. Even for that third loop, this inner loop, okay, if you take the line integral, of dl for the third loop, that means this will be equal to what? This will be equal to twice the circumference of the third loop, which is equal to what? Twice pi r3. So that is the way how to write. Okay? So from here, that means a line integral of loop 1, this will be equal to 1. This will be equal to twice pi r1, and this will be equal to mu naught into 0. Okay, mu naught into 0 will give us the value which is equal to 1, which is equal to 0. So from here, it is very obvious that the magnetic field, if you cross multiply this side, this will give you the value of 0. So magnetic field due to the second loop, that means there will be no magnetic field on the first loop, okay, for the point which is outside. Then if you consider another case for the loop, for that point number 3, which is for the third loop, for that point Q, okay, which is point Q, which is inside. Okay, so from here, that means line integral of B dot dl, this will be equal to 1. B bar dot dl bar, okay, B bar dot dl bar. So this will be equal to mu naught. What is the current on the third loop? That means the current on the third loop will be I3, but that value, mu naught I3 will be how much? Will be equal to 0, since there is no no current. Then this B will be constant. Okay, so we'll take out. So you are left with what? You are left with a line integral across the loop 3 of dl. But this integration over that dl, okay, I have explained that integration over that dl, let us just recall the integration over that small surface. This is that small surface. Okay, this is that small surface. So over that loop number 3, that means line integration will be what? Will be twice pi R3. Okay, twice pi R3. So over here you write twice pi R3. And the product of that will be equal to 0. So from here, if you cross multiply, okay, if you cross multiply that twice pi R cube to the denominator of the right hand side, you will get it to be equal to 0, which means that the magnetic field across this second loop, okay, the magnetic field across that third loop, the magnetic field across that third loop also will be equal to what? 0, which means that from these two relations, okay, from equation 1 and equation 2, it is obvious, okay, it is obvious that there is what? It is obvious that there is no contribution to the magnetic field from the loops 1 and 3. So for these regions, which means for the regions outside the toroid, okay, I have a toroid like this. Okay, this is the toroid, and I have those loops which are formed. Okay, and then from here, for the region which is outside the toroid, and for the region also which is outside the toroid, okay, for those points P and Q, that means there will be no. That means over here at these points, magnetic field will be equal to 0. Even at this point Q also, magnetic field will be equal to 0. Only for points which is inside the toroid, only for this point, okay, if I construct over here, this will be inside the toroid. Only for this point which is inside the toroid, okay, only for that point which is inside the toroid, this B will be non-zero, which will be not equal to 0. So likewise, from there, if you apply Ampere's circuital law for the third loop, okay, if you apply Ampere's circuital law for the third loop, that means that expression can be written as, okay, so from here, this will be line integral for what? For the loop 2. So from here, it is already known that the magnetic field will be non-zero for the second loop, okay, for the second loop. So from here, line integral will be equal to what? Mu naught, okay, mu naught I, okay, mu naught I. But if you look from this particular network, okay, if you look from this particular network, since okay, if you look from that, if you look from this particular diagram, okay, if you look from this particular diagram, if there are n number of turns, okay, if there are n number of turns, then that means it will be what? It will be mu naught n. If you have only one turn, that means you can simply write, okay, you can simply write mu I. But over here, due to this loop number 2, for this loop number 2, that means how many turns are there which contribute to the magnetic field? It will be mu naught n I. Okay, it will be mu naught capital N I. So from here, this you have to write mu naught capital N I. So mu naught capital N I. Where capital N is the total number of turns, and over here, this I is nothing but the current. Okay, that I is nothing but the current which is enclosed. Okay, current enclosed by that loop 2. Okay, by that loop 2, or that Amperean loop 2. Then from here, okay, that means since the magnetic field is always constant, so we can take this B outside. Always keep in mind that the magnetic field for a toroidal solenoid, or if it is a solenoid, is always uniform and constant for regions. Okay, it is for regions which is inside. Okay, if it is regions for inside the toroid, okay, inside the toroid, the magnetic field is also is always constant. So the magnetic field B is always constant inside the toroid. So we can take this B outside of the integral sign. But another important analysis has to be determined. It has to be determined over here. See, over here, this is the line integral of what? Line integral of the second loop. And from here, since this is the dot product, so you have to write what? BDL 1, cos of the angle. So what is the cos of the angle between those current elements? See, from here, okay, you have to look from the figure again. Okay, from the figure again. So from the figure, okay, we have represented that since this is what? This is the direction of current. If I consider a small element, okay, if I consider a small element. So over here, see, if I consider this as the element, that means that will be what? That will be dl. And since over here I can construct a tangent, that means this will be what? This will be dl bar. But it is obvious, okay, that the direction of db, where is the direction of db? The direction of db is the same with respect to this dl. So which means over there, that the direction of db also, the direction of this db also will be what? Will be in the direction of b also will be in the same direction. So which means for this second loop, if I consider this small element over here, if I consider that small element dl, then the line drawn across that small element will be what? Will be this dl bar. Since the direction of the magnetic field, okay, since the direction of the magnetic field is in this direction, it is in that direction, this will be the direction of the magnetic field. So it is obvious that if I draw a tangent across this element, that will give us what? That will give us the direction of what? That will give us the direction of what? Magnetic field, which means that the direction of the magnetic field and the direction of what? And the direction of this element dl are in the same direction, which means that in this case, okay, for this element, which means that in that case, for that element, dl will be in the same direction, as well as, okay, as well as this b also, that b also will be what? That b also will be on the same direction. So if dl and b are in the same direction, so it is obvious from there that the angle theta, okay, that theta over there will be how much? That theta over there will be equal to how much? Will be equal to 0 degree. Since they are in what? They are in the same direction. Okay? Since they are in the same direction. So this is very, very important to visualize. Okay, to visualize from the diagram. Okay? So from there, it is very obvious that the angle between dl and b, the angle between that dl and b is equal to what? It is equal to 0 degree. Okay, it is equal to 0 degree. So here our is right, 0 degree. Since, okay, b and dl, you can write that they are parallel. Okay, you can write that they are parallel, or they are in one, or they are in the same direction, or they are in the same direction, or they are in same direction. Okay? Same direction. So this is very, very important, which allows us to write this. Always remember that this is the vector form of dot product, and this we have represented in the scalar form. So from here this will be mu naught ni. Then from here cos of 0 will be equal to 1. So from here you have only line integral of b dl. This will be across loop 2. Then from here this will be equal to mu naught, okay, mu naught ni. Then from here b will be constant. Okay, b will be constant throughout all that loop number 2. Across that loop number 2, the magnetic field across all those points with b across all those points will be what? Will be constant. So we can take outside. Then we are left with integration over dl. So this will give us what? Mu naught n, capital I. Then this will be for integration over what? Over the second loop. But from there, if you take over, if you consider for that second loop, I have that center O of the toroid, and this will be r as the radius. So if I sum over all these small elements, okay, if I sum over all those small elements, that means if I sum over all those dl, that means summing over all those dl's, okay, summing over all those dl, it will be equal to what? It will be equal to twice pi r, and this is nothing but the circumference of that second loop, okay, of that Amperian loop. Circumference of what? Of loop 2, okay, of loop 2, or second beam, okay, lead to or second beam. So from here, okay, we can deduce this further. That means this will be equal to twice pi r, and that will be equal to mu naught capital N I, and from here, that means this value of B, okay, that value of B will be equal to what? Will be equal to mu naught capital N I divided by 1, divided by twice pi r. But, okay, but also I have also explained to you that the number of turns per unit length will be what? Will be small n, will be capital N divided by capital L, which means that this capital N, which is the total number of turns, is the number of turns per unit length into the length of that solenoid, or the length of that toroid. But the length of that toroid, okay, how much is the length of that toroid? The length of the toroid is twice pi r. So from here, this will be n into twice pi r. So from here, we can rewrite that value of n, substituting these values, okay, substituting that value. So from there, which implies that this b, this will be equal to mu naught. Using this value of capital N, that means we can write over here small n, okay, small n, twice pi r, then you have I, and over here also you have 1 divided by twice pi r. So from here it is obvious that some of the terms get neutralized, twice pi and twice pi gets cancelled, so which means that this expression, okay, can be reduces to this form. This b will be equal to 1 mu naught n I divided by 1. It will be equal to simply mu naught n I. It will be equal to simply mu naught n I. So that is why, if you recall from the equations with respect to the magnetic field due to a solenoid, it will always be given by this formula. So this is the expression. Okay, this expression is very, very important, which means that the magnetic field due to the solenoid is directly proportional to the current which flows through the toroid, and number 1, and this B is also directly proportional to the total number of turns per unit length. More is the number of turns, more will be the magnetic field. More is the magnitude of current, more will be the magnetic field. So from here, this expression, okay, this expression gives the magnetic field due to the toroid. Okay, and from here, always keep in mind that the direction of the magnetic field can be determined by the right hand thumb rule for circular leaves, and in this case, it will be L1. It will be in the clockwise direction. See, okay, why is it in the clockwise direction? Okay, why is it in the clockwise direction? So, if you use your right hand, okay, from here, the curl of the fingers, okay, the curl of the fingers indicates what? The direction of your magnetic field. So from here, see, this is the direction of what? This is the direction of flow of current. Okay? This is the direction of flow of current, or flow of magnetic field. Okay? This is the direction of movement of magnetic field. This is your dB. So dB in this case will be 1. What is this direction of dB? This direction of dB in this case will be 1. It will be clockwise in nature, depending upon this way in which the current is moving. Okay, that end of the solenoid, or that end of the toroid where the current enters, okay, it will behave as the south pole. That end of the toroid where the current leaves, that will behave as what? That will behave as the north pole. So also from here, the nature of the magnetic field inside the toroid, okay, it will be what? It will be uniform. First, it will be uniform and it acts tangentially. Why it acts tangentially? Over here, I have discussed very, very carefully. Okay, at this particular point, it acts like a tangent. Even if I consider at this point, okay, what if I consider this as what? This as dl. So that will be the direction of what? This will be the direction of dl. So what will be the magnetic field at that particular point? So at this particular point, again, I have to draw what? I have to draw a tangent. So that will be direction of dB. So at each point within the toroid, so the magnetic field, it will always act tangentially. Okay, it will always act tangentially, and it is one, it is clockwise in nature, and you can determine that by the right hand thumb rule for circular leads. So from that figure 2, I have explained this point number 1 for regions where the current enters or goes inside. Okay, for the regions where the current enters or goes inside, it is denoted by cross mark, and for regions where the current it appears to leave, okay, or comes out, okay, if it leaves or comes out, then they are labeled by what? Then they are labeled by those dots. Okay, they are labeled by dots. Okay, the dot mark. Okay. Similarly, the Amperian loop are constructed as it encloses the region of the toroid inside as well as outside. Then from here, keep in mind this point number 3 is very important. Point number 3, always it is very important. You should always remember that that end or that loop of the toroid where the current enters, that will behave as the south pole. Okay, that end of the loop or that end or loop of the toroid where the current goes or comes out or leaves, that will behave as what? That will behave as the north pole. Just go through the entire lecture so that you will have a clear concept and you will have a clear understanding about what I have explained. Just go through so that all your confusions will be clear. Until we meet again, thank you.